everybody. In the last class, we discussed a necessary condition for a function f of z to be differentiable or to be analytic. What was the condition? The condition was that if a function if is differentiable, then it satisfies the Cauchy-Riemann equation, and the real and imaginary parts are also differentiable. And this is the converse of the previous theorem. It says that the condition under which this is the condition under which a function f of z becomes differentiable or analytic. Over here, the statement is given in terms of differentiability. So over here, we are given that if the real and imaginary parts, these two functions, u and v of the function f of z, are differentiable at a particular point x comma y and satisfy the Cauchy-Riemann partial differential equation, that is partial derivative ux is equal to dy, the partial derivative dy, and the partial derivative uy is equal to negative of the partial derivative dx. Then we are going to prove that this function f of z is a differentiable function at the point z is equal to x plus iy. So this is just opposite category of result. Over here, the real and imaginary parts are given to be differentiable. Okay, the real and imaginary part are given to be differentiable at the point x and y, satisfying the Cauchy-Riemann equation. Then we are going to show that f of z is differentiable at the point z is equal to x plus iy. The proof is easy, and this is one of the second important theorem in this chapter that can be selected in exam. I am writing the detailed calculation, only the calculation portion over here. So this is the sufficient condition. Let me just cut and paste in this next line. Over here, we are going to prove this theorem, and I am not writing the detailed language over here. I would say in my words, but I would write only the mathematical portions. So we are given that the functions u and v, these two are differentiable functions, and as because these are two differentiable functions satisfying the Cauchy-Riemann equations, we have to prove that this function f of z is analytic at the point z is equal to x plus iy. So as because the function u is a differentiable function, we can write that u of x is u of x plus p comma y plus q minus u of x comma y, that would be is equal to the partial derivative ux multiplied by p plus the partial derivative u suffix y multiplied by q plus maybe certain epsilon 1 into p plus say epsilon 2 into q, where epsilon 1 and epsilon 2, this epsilon I, you can say I, this epsilon I, or rather we write epsilon k because I refers to root over of minus 1. Epsilon k tends to 0 as p comma q tends to 0 comma 0. So this is the definition of differentiability for the function for the function u at the point x comma y. Okay. Similarly, for the function v, we will have similar expression v of x plus p plus y plus q minus v of x comma y, that would be is equal to partial derivative vx into p plus partial derivative dy into q plus maybe some other kind of epsilon, maybe epsilon 3 into p plus epsilon 4 into q, where is epsilon k tending to 0 as pq tending to 0 comma 0 comma, we can say that k is equal to 1 comma 2 comma 3 comma 4. So all these four different epsilon, all these epsilon are tending to 0. Okay. Now let us let us write them as equation number 1 and equation number 2. So this is the first equation, the equation number 1, and then the second equation we refer them as equation number 1 and 2. Now we have to show that the function f of z is differentiable, and in order to do this, what we need to compute? We need to compute f of z plus h minus f of z divided by h. We need to show that this is tending to f dash z. This is tending to certain definite number as h tends to 0, as h, and what is h? H would be is equal to p plus iq tends to 0, the complex number 0. Now what is f dash z? You see, we already proved the expression of f dash z in the previous day. We proved that in this previous result, we already no, we did not prove the expression. Sorry. Over here, we proved the expression in a different fashion. We considered f dash z. This where is f dash z? We considered this f dash z in the previous proof. F dash z is equal to alpha plus I into beta. And finally, we proved that alpha is equal to ux and beta is equal to vx. So we can write that f dash z, this is the previous proof, previous theorem in the last class. We can write f dash z is equal to alpha plus I into beta, that is equal to alpha means the partial derivative ux plus I into beta means the partial derivative vx. Okay, so this is the expression of f dash z. Again, this expression of f dash z can also be written in this fashion. So you see alpha has a different value, say vy. Alpha plus I into beta. What is beta? Beta is equal to, from this relation, beta would be equal to minus uy. So with this negative sign, we will have this kind of expression. Got it? So over here, we can say that f dash z is actually this kind of expression ux plus I into vx. This is, you see, this is actually an expression in terms of the partial derivative with respect to x, and this is an expression in terms of the partial derivative with respect to y. Okay, so you see, in place of f dash z, our target is to prove that this quantity, this ratio f of z plus h minus f of z divided by h, this ratio will converge to this expression ux plus I into vx. And what is this? This expression is nothing but is equal to our f dash z. So this would be our main blueprint of the proof. Our target is to show that this ratio will converge to this complex number or the complex value function ux plus I into vx, and that is actually our f dash z. If it is possible to show, then we can conclude that the derivative of the function f, that is f dash z, exists, and f dash z is equal to ux plus I into vx. Got it? So we are going to show this much only. Alright, we are going to show this result. So we start with this ratio. We start with this ratio. And what is this? We can write this expression is f of z plus h. You see, we have this information that f of z, this expression f of z is equal to u of x comma y plus I into p of x comma y, and f of z plus h means f of z plus h will be is equal to f of u of x plus p comma y plus q, my plus I into p of x plus p y comma y plus q. Okay, so over here in place of this f of z plus h, we can write this expression minus this kind of expression. So this expression with this would be negative sign. And what is h? H is equal to, this is taken as p plus I. So in place of h, I am writing p plus I. Now we shall use these two relations, relation number 1 and relation number 2. So yeah, over here you see this can be written in this way. This can be arranged in this way. Just if you consider the real part, this can be written in this fashion, and I can now be taken common. Over here, this will be is equal to, this is the real part. This is the real part, and this is the imaginary part. Now over here you see this ux plus p comma y plus q minus ux comma y. This left hand side, this expression can be written by this kind of expression. It can be replaced by this kind of expression. So I'm just copying and pasting over here. So over here, this is the first part, and from equation number 2, this difference, that is actually delta v, this difference can be written in this way. So I'm just copying this one and pasting it over here. Now I'm trying to arrange. These results. How to arrange these results? I'm trying to write this expression in this fashion. You see. Firstly, let me omit this these expressions. So I will be multiplied by all these terms. Okay. Now over here you see this this expression, the partial derivative. I am trying to identify all the terms which does not contain epsilon, any of this epsilon. Okay, so I'm trying to separate these two terms and these two terms, because these four terms are actually epsilon related terms, and these other four terms is a free of epsilon. So let me copy and paste in the next line. So over here, this is the term, and I'm just shifting it over here. These four terms does not depend upon epsilon, and these remaining terms are dependent upon epsilon. Now you see, you look at these four terms. These four terms. Let me manipulate it in this fashion. Over here, I can take this p common from these two terms. So rather I'm writing them over here. So after taking this p common, what we shall have? We shall have this type of expression, ux plus I dx, and from these two expression, I am taking say something like that. I'm taking this q as a common quantity. Q. Let me take this expression q. Now I would make certain modification. Actually, uh, my target is to cancel from this first part. My target is to cancel this expression p plus iq. How can we cancel this expression? You see, we are given that these two functions u and v, both of these two functions satisfy Cauchy-Riemann equations. Okay. So over here, as per the Cauchy-Riemann equation, what is Cauchy-Riemann equation? The Cauchy-Riemann equation, Cauchy-Riemann equations. The Cauchy-Riemann equations are these two equations: ux is equal to vy and uy is equal to minus vx. So these are the Cauchy-Riemann equations. And in place of, if you look at this expression, this is the partial derivative with respect to y. By the help of Cauchy-Riemann equations, I am trying to convert this expression into an expression involving partial derivatives with respect to x only. Clear? So now in this next line, I am going to apply Cauchy-Riemann equation in this expression. Okay. So ux is equal to vy. So this, in place of vy, I am going to write ux, the partial derivative x, and uy is equal to minus vx. So in place of uy, I am going to write minus v suffix x. Here, now you see this minus, this negative minus 1, basically minus 1 is multiplied by vx. So this minus sign, this can be written as square of this iota or I square. And therefore I can now further take small I common out of this expression. So I am taking this small I common out of this expression. So we shall have this kind of expression, ux plus I into vx. So let me arrange them in this fashion: ux plus I into vx. Okay, ux plus I into vx. Here, therefore, in this next line, you see over here ux plus I into vx can be taken further common. So we are taking this expression ux plus I dx common, and ultimately we will be able to write the entire expression in this fashion. And now if we decompose it, if we decompose this expression, then what we observe, you see, this is the first term, plus the second term, this would be the second term. Okay, this would be the second term. In fact, all these terms can be further decomposed. I shall decompose them further, but over here you see p plus iq and this p plus iq will get cancelled, and therefore we just cancel them, because ultimately we will have to take p and q tending to 0, 0. So p plus iq will be not equal to p. Therefore, we shall have this type of expression, and these four terms can be further written in this way: this expression plus this epsilon 2 into q divided by p plus q plus I into epsilon 3 into p divided by p plus iq, and the last expression would be is equal to over here I into epsilon 4 into q divided by p plus iq. Here, now I am trying over here, this is the left hand side. I am trying to shift this expression on the left hand side. Okay, so we can now write what was the left hand side. The left hand side was is f of z plus h minus f of z divided by h. This is the left hand side minus this expression partial derivative ux plus I into dx, that would be is equal to this, right, and this four terms. And now if we take the modulus of this expression, then this would be is equal to modulus of the right hand side. All right, and that modulus, this quantity, would be less than is equal to modulus of each and every such term. That would be is equal to modulus of first term plus modulus of second term plus modulus of third term plus modulus of fourth term. All right. Now over here, this epsilon can be written in this way: modulus of epsilon 1 over here. This can be written as modulus of epsilon 2. This I into epsilon 3. This can be written as modulus of I into epsilon 3, and I into epsilon 4 can also be written as modulus of I into epsilon 4. Here, now you see over here this expression modulus of I into epsilon 3. What is this? You see, modulus of I is actually is equal to 1. So I should rather write it in this way, that becomes is equal to modulus of I into modulus of epsilon 3, and modulus of I, that is equal to 1. Here, similarly, over here, I should write modulus of I into epsilon 4. Again, this modulus of I is equal to 1. So, in place of this kind of expression, I can put modulus of I is equal to 1. So, 1 into this kind of expression, that would remain the same. So, we are not writing this extra multiple 1. I'm just skipping this one. So we have this type of expression. Now you see over here we can say that this modulus of p, so modulus of p is less than is equal to, or you can say modulus of p is equal to this square root of p square, positive square root of p square, and that is less than is equal to square root of p square plus q square, and that is basically modulus of p plus iq. And this implies that this kind of expression is p modulus of p divided by p plus iq is less than is equal to 1. Similarly, we can write over here. Similarly, we can write over here this modulus of q. This modulus of q. This modulus of q is less than is equal to square root of that is equal to square root of q square, and that is less than is equal to root over of p square plus q square. That is modulus of p plus iq, and that would give us q divided by modulus of q divided by p plus iq is modulus that should be less than is equal to 1. So you observe that these four expressions are all less than is equal to 1. Therefore, you can write this expression is less than is equal to modulus of epsilon 1 plus modulus of epsilon 2 plus modulus of epsilon 3 plus modulus of epsilon 4. 3 plus modulus of epsilon 4. Clear? And therefore, we all know that all these four epsilon are tending to 0 as this h or p plus iq, whatever you write, h that is equal to p plus iq, p plus iq is tending to 0. Okay, so what you observe, we finally got the expression that this expression is also tending to 0 as h tending to 0. So you can say that this expression is tending to 0 as h tending to 0. Here, as h tending to 0. What does it mean? It means that this expression is tending to this expression, or we can say that limit. Let me write it in this fashion: limit h tending to 0, this kind of limit of this function f of z plus h minus fz divided by h, this limit exists and is equal to this value ux plus I into vx. Here, therefore, we can say that the function f is differentiable. Existence of this limit means the function f is differentiable, and this is nothing but is equal to f dash z. This is nothing but is equal to f dash z. Therefore, we can say that the function f is differentiable at the point z or x plus I. Okay, so this completes the proof of this sufficient condition. Now let's discuss a little bit about the analytic function, because I already introduced the definition of analytic function in the previous class. I told you that if a function is defined on certain domain, open connected set, and at each and every point, if the function is differentiable, then we say that the function is analytic throughout the domain, suppose D. This was the definition of analytic function. But sometimes we try to define the analytic function at a point. Here we sometimes try to define analytic function at a point, at a single point. Now, how to define analytic function at a single point? In that case, we say that suppose we have a point, maybe say the point P. We say that the function f is analytic at the point P if there exists a sufficiently small neighborhood of the point P at each and every point of which the function is analytic. Here, at each and every point in the neighborhood of this point P, the function should be analytic. If it happens that there exists a sufficiently small neighborhood, what kind of neighborhood, that doesn't matter. It may be circular neighborhood, it may be any kind of arbitrary shaped neighborhood, but neighborhood is always an open set. We all know that. So what we need to do, we need to, if it is possible to find a sufficiently small neighborhood of this point P at each and every such point, the function is analytic, then we say that the function should be analytic at this point P. Here, so this is the analyticity of the function at a point P. Now you see, we introduced two results. One is a necessary condition for differentiability, and another is the sufficient condition of differentiability. In the last class, we introduced this theorem, that is actually the necessary condition for differentiability. Now, if the same kind of result is to be written regarding analyticity, how can we modify this theorem? More or less, the proof would be same. The total computational steps would be same. Just we need to add one extra condition, and just how to modify this theorem. This is the necessary condition for analyticity. We are given that f z is differentiable. Now, in place of differentiability, we would say that if f of z is analytic at the point z is equal to x comma y, then the real and imaginary part ux and vy are also differentiable. This much would be differentiability, because analyticity is related with a function of complex numbers. Here it is not, so far at least I am not discussing any idea of analyticity for function of two variables here. So this u and v should be differentiable, and this ux is equal to vy and uy is equal to vx at the point x comma. This much is the modification. Similarly, if we need to modify this theorem, this statement of this sufficient condition, then how to write the statement? you see, if u and v are differentiable at the point xy, rather we should say at every point, okay, at every point in a neighborhood of x comma y, because here we should finally say that the analyticity is defined at the point. At the point means we should have to consider on a neighborhood of that point. Hmm? So if u and v are differentiable at every point in the neighborhood of AB, in the neighborhood of this point x comma y, and ux is equal to py, dy is equal to vx at the point x comma y, then f of z is analytic at the point z is equal to x plus iy. Here. So this and this you see over here, this in this is the necessary condition. You could also modify it in this fashion at the point x comma y, in case of this point, at each and every point in the neighborhood of x comma y, at each and every point of all the points in the neighborhood of x comma y. You can modify these two theorems in this fashion. Remaining computational steps would be exactly same. No change is there. Just a little change is to be introduced in this necessary sufficient condition for analyticity. Okay. So this much I wanted to tell you about the analyticity. Here, now today I am just going to discuss few results regarding the analyticity, or regarding the analytic function. It is very interesting to observe that there is a theorem. I am just writing the statement of this theorem because proof of the theorem is not possible at this level. There is a very interesting theorem. It says that if a function f of z, function of complex variable, suppose f of z is analytic at a point, say x comma y, or it may be an analytic on a domain D. You can also write it in this fashion, on a domain D. Then the derivative if there z is also analytic z on D, on this domain D. If a function f is analytic in a certain domain D, then its derivative f dash z, that is also analytic in the same domain D. Here again, you see, we can apply this result on the function f dash z as well. That means if a function f dash z is analytic, then its derivative, that means f double dash z, that should also be analytic, and we can continue this technique for any positive integer. So we can say that if a function f of z is analytic, then the derivative, nth derivative fn, okay, this fn, you can also write it in this way, fn z is also analytic on D for n belonging to the set of natural numbers capital N. Here, so for all positive integers, these derivatives exist, and all such derivatives are also analytic at the point D. That is a very powerful concept of analyticity, that if a function is analytic, then it's all the derivatives of any order, these are all analytic functions. That is one of the important property of analyticity. Now you see, if the function f is analytic, that means if it is a differentiable function and its higher order derivatives are all analytic, then what is, let us first just simply consider this first order derivative f dash z. F dash z is equal to ux, that is actually a function of x comma y, plus I into the partial derivative x. That would also be a function of x. Hmm. It is if it is analytic function, then its partial derivative ux, and you see, if it is an analytic function, I told you that analyticity means it should be a differentiable function. It is always mean that if a function is analytic, then it must be a differentiable function. Because analyticity means along with the point, the function should be differentiable in a neighborhood as well. So if it is analytic, if the function f is analytic, then its derivative f dash z is also analytic. That means it is a differentiable function, and we know that differentiable function is always continuous function. Hmm. So this function f dash z should be a continuous function. That means this real part and the imaginary part, all of them must be continuous function. Hmm. And we would continue this process. You see, then what would be f dash z? Sorry, f double dash z. Hmm. F double dash z. That would be further partial derivative with respect to x again. You see, if we call an interesting result is that, so if suppose w is equal to say f of z, and what is this? This is actually u plus iv into p. V is a function of x comma y, and u is also a function of x comma y. Then what is this f dash z? This f dash z should be is equal to dw dz. So dz. This should be is equal to dw dz. Okay, this dw dz should be is equal to f dash z. And if you look at this expression, that this is actually the partial derivative del x. Partial derivative of del x of what? Partial derivative of u plus iv, isn't it? This is the partial derivative with respect to x. This is the partial derivative with respect to x. So this is actually the partial derivative of u plus iv with respect to x, and that is equal to the partial derivative with partial derivative of what? Partial derivative of w. So you see, dw dz can be written as del w del z. So if further we continue this process, so we can say that this ddz operator, we can say that this kind of ddz operator, this ddz operator, this is nothing but is equal to del x operator. Okay, this ddz operator is nothing but is equal to del x operator. So f dash z, what is f dash z? F dash z is actually is equal to ddz of further f dash z, f double dash z, this second order derivative, that should be is equal to ddz of f dash z, and that is equal to ddz of what is f dash z? F dash z is equal to this expression. This kind of expression, partial derivative ux plus I into dx. I am not writing these expressions. This would make the expression a bit simple one. And what is this? What is this ddz? Ddz is equal to the partial derivative operator del x. So you see this higher order, the second order derivative would be is equal to u xx plus I into d xx here. So you see over here, if a function is analytic, it's any order partial derivative is also analytic. That means it is a continuous quantity. So f dash z is a continuous quantity, and it means that this partial derivatives uxx and vxx, these are all continuous quantities. Similarly, we can prove that all the other mixed order partial derivative, that would also be a continuous quantity. And in such cases, we can say that Cauchy-Riemann equation is satisfied. Cauchy-Riemann equation means this equation, ux is equal to vy and uy is equal to vx. All these relations should be satisfied. Now please if you look at this expression a bit carefully, differentiate this relation with respect to x and differentiate this relation as well with respect to y. I am differentiating this first relation with respect to x. What we get? Uxx, the second order partial derivative, Uxx, that should be is equal to Pyx. And if we differentiate this expression, Uy is equal to minus Vx, then what we shall have? Uyx is equal to minus Vxy. And if the partial derivatives of Vxy or Vyx, these are all continuous, then one can prove that we can interchange the order of this partial derivative. These are two standard results in the functions of several variables. I am not going to state all these results. This is about the interchange of the order of mixed partial derivatives. Mixed partial derivatives. That it says that if the higher order partial derivatives, this kind of partial derivatives, the yx and vxy, these are all continuous, then one can write that vyx is equal to vxy. And therefore, so what we can write that this uxx plus uyy. What is uxx? Uxx is equal to vxy and uyy is equal to minus of vyx. And as because these two expressions, these two mixed partial derivatives are equal, therefore we can say that this is equal to 0. Clear? Not only this one, you can similarly prove just by differentiating this relation with respect to y and differentiating this relation with respect to x. You can similarly prove that v of xx plus v of yy, that would also be equal to 0. And these two relations, these two equations, uxx is equal to 0, uxx plus uyy is equal to 0, and vxx vyy is equal to 0. If you look at these two expressions, these are actually two different partial differential equations. This is a partial derivative. This is another partial derivative. So this is a partial differential equation. Here, similarly, this differential equation is a similar kind of partial differential equation. Here, and these two partial differential equations are called Laplace equation. These are called Laplace equation. The partial derivative, the double derivative with respect to x plus the double derivative with respect to x plus double derivative with respect to y. This kind of equation is called Laplace equation. And if a function satisfies this Laplace equation, along with the fact that the partial derivatives of that function are second order partial derivatives, up to second order partial derivatives of that function are continuous, then such functions are called harmonic functions. This equation, Laplace equation, is also known as potential equation. And these harmonic functions are also known as potential functions. Clear? So this kind of equation, that means if remember very carefully, because you generally make a mistake. In most of the books, it is written as that if a function satisfy this Laplace transform, satisfy this Laplace equation, then that function is harmonic. The definition is wrong. Clear? That harmonic function, that if a function, if a function satisfy the Laplace equation, and if its partial derivatives up to second order are continuous, then such functions are called harmonic functions. Clear? So please be very careful about this definition. Generally, this is sometimes given as a short question, like a question of 2 marks. Certain function is given, and you need to verify whether that function is harmonic. So over here, in that case, you need to verify that this kind of partial derivatives uxx plus uyy is equal to 0. This kind of equation is satisfied, along with the fact that their partial derivatives are continuous. Clear? Their partial derivatives are continuous. Then only we say that particularly that function is an analytic function. Clear? So you please be very careful about this kind of result. For example, let's discuss one example, a very short example. Say, suppose let u is equal to, say, x cube minus 3xy square, xy square. Now we need to check whether this is any harmonic function or not. We need to check whether this is a harmonic function or not. Then how can we check? You see, we can easily compute the partial derivatives. Here u x would be is equal to 3x square minus y square minus 3y square. U partial derivative uy, that would be is equal to simply minus 6xy. Okay. Now uxx, the second order partial derivative, that would be is equal to 6x, this much 6x. Then u yy, that would be is equal to minus 6x here. Then u xy, what would be u xy? That means ux has to be differentiated with respect to y. So it should be minus 6y, and you can check that when this uy is differentiated with respect to y further, you again will get minus 6 only, 6x. They make correct. No, sorry. This uxy is equal to minus 6y. Is it so? Ux, then y, it is equal to minus 6y. Fine. So, and what about sorry? What about this uyx? Uyx, whenever it is differentiated with respect to x, you will get minus 6 into y. That is again is equal to minus 6 into y. Here you see all these quantities, these partial derivatives up to second order, these are nothing but polynomial like quantities. So we know that polynomial is a continuous function. So from these expressions, as because you can write that as because these are polynomials, therefore this all these partial derivatives are continuous. So we can say that as these are polynomials, so all of them are continuous functions. And if you check over here that this uxx plus uyy, that is equal to 6x plus, not plus, minus 6x, that is equal to 0. Or u satisfies the Laplace equation. Hence u is a harmonic function. So in this fashion you will have to conclude. Here. So that's all for this lecture. Thank you for being with us.